Okay, 3 more minutes, all right? Then I will choose 2 person to give me answer for the first and the second part. Okay, so can we have anyone who would like to volunteer first? Is there anyone? Anyone willing to volunteer, or do you want me to pick a name? All right, there's nobody to volunteer. Can we have Amanda for the first part to calculate the rate constant? And maybe we can have the next person, Adisti Ekaputri.
Okay, doctor.
Adisti, you can answer the second part. All right.
All right.
Okay, so can we have the answer for the first part?
I'm sorry, doctor. I'm answer no number 4 2. Okay.
Okay. Yes, Adisti number 2. Just now number 1 was where's the name has gone missing. Who was supposed to answer number 1 just now? Amanda, yes. Where is Amanda? Right. Amanda is missing. Just now she was here. Okay, can we have someone else to answer number 1?
Yes, I have written number 1
Akib.
answer.
Akib, is it?
Yes, can I?
Sure,
Yes,
sure.
can
Please,
I show
please.
you?
Yes, please. I will stop share and you can share your screen. Yes. Please, Akib, go ahead.
Is it visible?
Not really. Maybe it needs a bit of time for it to. Okay, maybe you can explain what have you done.
Is it visible or not?
We can roughly see it. Yeah. Yeah, it's okay actually. It's not too bad.
Okay.
Okay. Yes, can you explain?
Yes. First, we write the equation. Rate is equal to K HBR twice, and then we have to first find the rate constant K. K is equal to rate over HBR concentration square. Then we put the values for rate, and the value for rate is 3.5 multiplied by 10 raised to power minus
Hah?
4, and
Apa?
the
Apa,
HBR
Pak?
concentration is 1.
Belum, masih input DL.
Oh dear.
I think there is some noise behind.
Yeah, hold on. Yeah, muted. Okay, muted.
Okay, then we put the concentration for HBr, that is 1.20 mole per decimeter cube, and scare, that is twice, and then we take the scare, it becomes 2.4, and then we divide it with the rate value, then we have last 1.45 multiplied by 10 raised by minus 4, then it becomes mole, cancel mole, and it becomes mole per mole, and a decimeter cube, and per second at the end. It becomes the rate constant value K.
Akib, all right, your method is correct,
Yes.
but I have a feeling that you might have gotten the calculation wrong. Maybe you can divide again to see what do you get. Okay, because when you take 3.5
Oh,
times 10 power of negative 4 divide by 1.2 square, you're supposed to get 2.43 times 10 power of negative 4. So I think there's a mistake there. You can double check the answer, but your method is correct.
okay. I will
Okay?
again calculate.
Yeah, that
Okay.
is fine. That is
Okay.
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 But your method is correct. I hope
Okay.
everybody can take note of the method. But the final answer is 2.43 times 10 power of negative 4. Okay, and your units are correct. So good.
Okay.
Okay, good job. All right, can we have Adisti? Thank you, Akib.
Okay. I will again.
Yeah,
Okay.
it's okay.
Thank you.
It's okay. Thanks, Akib. Okay, Adisti, can you
Okay, dokter.
yes, give us the answer, share your answer for the second part.
I'm sorry. I will do share screen. Um, I'm sorry, dokter. Can I speak
Yeah,
bahasa?
sure. Yeah, can. You can
Okay.
speak bahasa.
Jadi soal nomor 2 itu ditanyanya adalah mol H plus. Jadinya yang pertama kita lihat dulu ada lajunya yaitu adalah negatif 1/2 HBr dibagi dengan delta T sama dengan konsentrasi H+. Di mana kita masukkan harganya yaitu negatif 1/2 dikali konsentrasinya kan sudah diketahui yaitu 3,5 dikali 10 pangkat min 4 sama dengan konsentrasi H+ dibagi delta T karena untuk menyeimbangkan antara yang di kiri dan juga di kanan, sebelah kanan. Oke, kemudian kita hitung negatif 1/2 dikali 3,5 kali 10 pangkat min 4 adalah negatif 1,75 dikali 10 pangkat min 4 sama dengan konsentrasi H+, karena di sini konsentrasi H+ dibagi konsentrasi delta T itu, delta T-nya sama dengan 1 detik. Kemudian untuk itunya Dan kemudian untuk liternya yaitu 1 liter. Kemudian negatif dikali negatif jadinya 1,75 dikali 10 pangkat min 4 dikali 1 sama dengan mol H+. Karena kan mol konsentrasi itu konsentrasi sama dengan mol dibagi dengan volume. Mol dibagi volume. Sorry, dokter.
Okay, never mind, Adisti. Actually, I think you may have misunderstood the question, but still, I think you did try your best, so
Okay.
it is okay. Now you can unshare your screen and I will share the answer. Okay, okay.
Okay, dokter. Thank you.
Thank you for trying. Thank you for speaking up.
Okay, thank you. I'm sorry,
Yeah.
dokter.
It's okay. Don't worry. It is okay to make a mistake. It's fine.
Okay.
Okay, you can unshare your screen. Okay, so I will share the answer so that everybody can take a look. Okay, thank you to what do you call Adisti and Akib for speaking up. All right. So the question for the second part, okay, the first one is okay, it's right, but the second one is actually just nothing to do with your rate. Actually, it's more of your understanding of if you remember, I did mention during the lesson. Okay, you need to sometimes calculate the number of molecules. So when it comes to calculating the number of molecules, you must immediately remember about your Avogadro number. Okay, so it's very simple, right? First, you have to remember your Avogadro law. Okay, it means that under the same conditions of temperature and pressure, equal volumes of different gases contain an equal number of molecules, right? So what it basically means is if the molecular weight of oxygen is 32, so 1 gram mole of oxygen has a mass of 32 grams and contains 6.02 times 10 power 23 molecules. So this one is actually, you should know already by now, all right? So the question gives you is 2 mole of HBr can give you 1 mole of H. So if you have 1.2 mole of HBr, then it becomes 0.6 mole of H. So you just times by your Avogadro number and you will get the number of molecules in 6 mole of hydrogen. 0.6 mole of hydrogen. Okay, so it's actually very simple, just to it is not really calculating the rate, but it's also there is chances for this kind of questions to come out. All right, so you can be asked to calculate rate and then you will be asked to determine the number of molecules and so on. Okay, so now now we can go into today's lecture. All right, I've already shared the notes with you. So in today's lecture, we're actually going into the part on initial rate method, on how you want to calculate your order of reaction. Okay, so what I'm going to do is, because actually today I am going to have some background noise in my house because there's some emergency renovation that's supposed to happen. So what I have done is last night I have recorded my lecture. So now I will play it so that I can mute my microphone so that you don't hear all the knocking sound at the back. All right, so you will listen to the lecture, but I will be here if you have anything. And after the lecture, we will try the question in the breakout rooms. All right, okay? Can, so now I will share the video, right, of our lecture that I did yesterday night, right? Okay, so I will play the video now. Please pay attention. This will be the full lecture for today. Yeah. Okay. Hi. So let's go into today's lesson. So it is a continuation of what we have studied from last week, right? So last week we were trying to compare the rates of different runs, and then we are trying to get the order of the reaction. Okay, and those are very simple methods, right? So today onwards, we will be looking at a few ways to actually determine the order of reaction. All right. So one of the first method will be the initial rate method, which we will be looking at in more detail today. All right. And there will be a lot of questions that we need to answer, and we will be going through those questions. I will give a lot of examples so that you actually can answer different types of questions that can be asked during using the initial rate method. All right. Okay. Now, moving on. Okay. Now, when we talk about initial rate method, it is basically what we are trying to do is, for example, if you have such a, what do you call, hold on, let me just change. All right, okay. So when you have a general equation like this, right? Okay, A, which is your stoichiometry, big A plus small b, big B, which is your reactant, your A and B are your reactants, to produce a stoichiometric value of C with the product C and stoichiometry D with the product D. Okay, so in this instance, when you take the order with respect to A, all right, when you want to calculate the order with respect to A, because you can see here there is actually two different types of reactants. So if you want to take with respect to A, you will carry out two experiments separately. Okay, so keep in mind when we talk about the initial rate method, we want to focus on one reactant first. All right, so when we are focusing on one reactant, so what we will need to do is we need to run two experiments, which is separate experiment, and in both experiments, you will be keeping your B concentration constant. Okay, so you only change the concentration of A. Okay, so that is the basis of your initial rate method. Okay, when you want to calculate, okay, you will need to run two or more experiments, right? Usually we will run two experiments, and then we want to keep one of the reactant constant, and we only change the concentration of one. Okay, when you want to calculate. So the species that you want to calculate, you will change. The species that you don't want to calculate, you keep it constant. Okay, you will see in a while why that is important, right? So make sure you keep the right species constant. Okay, so then we will determine the initial rate for both the experiment. Okay, and any change in the initial can change only be caused by the change in A and not because of B. Right, so that means any change in your initial concentration, all right, initial rate, it's only because of the change in the concentration of A and not because of B. So which is why we are keeping the B constant. All right. Now, to determine with respect to B, then you run another two sets of experiments, and this time you can fix the concentration of A. Okay, so that is how you can find both the order with respect to A and B. Okay, so that is the gist of it, general gist of it. Okay, right? Hold on, yeah. Okay. Right. Now, okay, all right, okay. So let me just change the point again. All right. Okay, so this is an example to show you how do you actually determine the what they call the initial rates, and also to use the initial rate in order to calculate the order of the reaction with respect to either NH4 positive or NO2 negative. All right. So in this experiment, your NH4 positive and NO2 negative are your reactants. Okay. So what you do is, if you can see in your first experiment, okay, you're using 0.0100 for NH4 positive, and for NO2 negative, you are using a concentration of 0.200. Okay, so take note on that. And then you see your second experiment, okay, you are changing the concentration of NH4 positive, becomes 0.0200 M, and here it's where it becomes important. All right, you can see here that the concentration is the same, okay, for NO2 negative. So that means now you are keeping it constant. Okay, now look at experiment 3. Okay, so experiment 3 also gives you similarly changing the concentration of NH4 positive and keeping the NO2 negative constant. Okay, now this table here is actually just to show you how does the initial rates differ, okay, as you change the concentration of one of the reactants. Okay, so I want to draw your attention to, now let's look at 0.01 NH4 positive. You can see that the observed initial rate is 5.4 times 10 power negative 7. Okay, and when you increase it to 0.02, okay, which means you double the initial concentration, okay, you can see that the rate also, okay, the rate here also doubles. Okay, can you see that? All right, okay. So when you double the initial concentration, okay, the rate also doubles. All right, now let's look at the third one. Okay, so the third one now also the same, from 0.02 becomes 0.04. All right, so again, you are doubling the concentration, okay, and you can see here the rate also doubles. Okay, so this observation is actually very important for you to remember, and this also will help you to understand the gist of initial rate method. Okay, so let's look at experiment 4 until experiment 6, right? So in experiment 4, what you're doing is, now you are keeping the concentration of your NH4 positive as constant, and you are changing your NO2 negative. So this becomes 0.0202, right? So you're keeping here constant, okay, between experiment 4, experiment 5, and experiment 6. But you are changing, okay, you are doubling, okay, again, now you're doubling your NHO2, okay, you are doubling your NHO2, all right, okay, can you see that? So again, let's look at the rate, does it affect the rate? So your rate also seem to have doubled, okay, can you see? Okay, times that by 2, and you times here by 2. Okay, all right, okay. So in this simple experiment using the initial rate method, so this is actually a very simplified way of showing up, all right. This is just to introduce you that how the initial rate method is going to be helpful to you in order for you to determine the order of reaction. Okay, so one of the summary that you need to know, okay, is when the effects of doubling of initial concentration, the effects are different when the order of reactions are different. Okay, so for different orders, the effects will be different. Okay, so of course, zero order, okay, if you remember, zero order will be rate equals to, okay, right, rate equals to K, remember? So the concentration doesn't matter, the rate is equals to K, right? So when that happens, when the concentration doesn't matter, then it is a zero order reaction. Okay, so in zero order reaction, even if you increase or decrease the initial concentration, it's not going to affect the rate. Okay, so when you go into first order reaction, okay, when in first order reaction is what we have seen, okay, in this example here, okay, in this example here, okay, this is a first order reaction, okay, first order reaction because the rate doubles, right? Now, if this was a second order reaction, then when you calculate, you will find that your rate actually quadruples, right? If it's a second order reaction, the rate actually quadruples. Okay, why? Because it is power of 2 now, right? And of course, if it is a third order reaction, the rate is increased 8-fold. Okay, so this is just a very brief, basic summary of what your initial rate method is all about, right? So it is important to have an understanding of how your initial rate changing your initial concentration of your reactants can affect the rate of reaction. And when you try to link it back to the order of reaction, every order will have different what they call reaction to the change in the initial concentration of your reactants. All right. Okay. So let's move on. Okay. So I think this part of the summary might not be in your notes. Okay. But I will update into the platelet later today. All right. Okay. So let's look at, okay, in order to continue to look at the question, all right, so let's look at one example of question on how we can use the initial rate method in order to solve our problem, all right. So look at this example here. So you have your A plus B to get your products, okay? So you want to use the initial rate method to determine the order with respect to A and the order with respect to B, okay? So this is the initial rate, okay? This is the initial rate, huh? Okay, this is initial rate, right? So you can see here in your first run, on the first experiment, your concentration of reactant A is 0.0100 and the concentration of reactant B is 0.0100. Right? Now, let's look at run number 2. Run number 2, the A concentration is 0.0200 and the B concentration is 0.0100. Okay? And from here, you can see for run 1 and 2, the concentration of B have been kept constant, right? And if you look at run number 2 and 3, for run number 3, the concentration of A is 0.0200 and the run concentration of B is 0.0200. So for experiment 2 and 3, A is being kept constant. Okay, so keeping that in mind, right? Analysis of this data using the initial rate method, the ratios of the rate must be taken into consideration when the concentration doesn't change. All right, okay. So assuming, all right, so anything or anyhow, you must be able to write out your rate equation at all times, right? At any point of time, you must be comfortable to be, when you look at a chemical equation, you must immediately be able to write out your rate equation. Okay, so rate equals to your K constant. Okay, then you have your A, right, alpha, and your B, beta. Okay, all right. So this must come very naturally, and you must always remember how to write. So most of the questions at the start, we will ask you to give us the rate equation. Okay, or we might give you the rate equation and then we ask you to calculate the rate constant. All right, or we will tell you specifically find the order for reactant A and order for reactant B and so on. Okay, so this is a very simple example, a very straightforward one, right? So like I said earlier, we want to compare experiment 1 and experiment 2. So how we do that is, okay, basically we want to take the rate, okay, the rate of your experiment 1, okay, and we want to divide it with the rate of your experiment 2. Okay, so, and this will be equals to, right, K, which will be the same, right, and then you have 0.01, okay, and alpha, and 0.01, okay, of your beta. Okay, this is from your experiment 1. Okay, and you will divide by your K, okay, and your experiment 2, 0.02, right, and your alpha, and 0.01, which is your beta. Okay, so that's what basically this is. All right, so you can see here, this is your rate from your experiment 1. Okay, and this is your rate from your experiment 2. Right? Okay, okay, from here, right? So when you do that, okay, you can easily cancel out this. All right, so now what you are left with is, okay, and also you will cancel out the K. Other than that, you also cancel out all the corresponding units. This is very important. Okay, when I think we have been mentioning this many times throughout this chapter. Units are very important in your rate calculation. So you must always remember how to find the final units for your rate equation and constant and so on. Right? Okay. Now, so coming back here, so you take 0.0347, you divide by 0.1694, and then here 0.01 over 0.02, and don't forget your alpha, right? Okay, now when you do that, what you will get is 1 over 2, all right? And then here, 1 over 2 alpha, okay? From here, you can easily tell your alpha must be equals to 1, all right? Because power, right? Power of 1. It cannot be any other power, because if any other power, then these two won't be the same, okay? So this is actually a very simple, very easy and straightforward answer, okay? So let us go into a little bit more complicated one, which will be the B, all right? Okay, let's go to B. Okay, now for the concentration of the rate or order for B, okay, when we are talking about the order for B, so now you take the experiment, okay, experiment 2, okay, the rate of experiment 3, all right? Okay, so you want to divide the rate of experiment 2 and experiment 3, okay? And then, of course, you have the reactant concentration for A in experiment 2, reactant concentration for B in experiment 2, divide by the reactant concentration for experiment 3 and experiment, the concentration for reactant B in experiment 3. Okay, now in this instance, okay, there's a slight typo mistakes here. Okay, this should be your beta, right? This should be your beta. This is not your alpha. Okay, now from this experiment, okay, we can cancel here. We can cancel here, and obviously we can cancel this whole thing. Okay, they can cancel each other, right? Because the value will be the same, right? But of course, yeah, K, don't forget your K. Okay, so now you have 1 over 4 equals to 1 over 2 beta. Okay, class, here there's actually a slight mistake, yeah? The one that should be cancelled is not this, right? The cancel should be here. And this one is 2 different values, so it should be dividing, yeah? So slight mistake there, just take note, yeah, all right? Right? So here is where we will be using your knowledge of ln, right? Your natural ln, right? So you ln both sides. Okay, when you put ln on both sides, so you will get ln 1 over 4 equals to ln 1 over 2 power of beta. Okay, so beta can bring down and then becomes ln 1 over 4 over ln 1 over 2. Right, so basically your beta is actually equals to ln A 1 over 4 over with ln 1 over 2. Okay, so this you can easily type into your calculator and you can get the values, right? So when you get the value, you divide and you will get 2. Okay, so now you know that your rate law can be rewritten. Okay, so you know your alpha is equals to 1 and your beta is equals to, all right, beta is equals to 2. Okay, so what does this tell you? All right, so that means your rate is K concentration of A times by concentration of B power of 2. So your A is first order. Okay, it is first order with respect to A and second order with respect to B. So overall order of the reaction is now 3. Okay, and from there, okay, now that you know your rate equation, you already know the overall rate order, okay, sorry, overall order, and also the order for your reactant A and the order for reactant B, you can now plug in all this information to calculate the rate constant. And you can choose any one of the runs, okay? Earlier we had 3 runs, right? So you can choose any one of the runs and you put in all the values that you have obtained, okay? So this is the initial rate form given in one of the runs, okay, run 1, yeah? And equals to K, and then the concentration of A, power of 1, concentration of B, power of 2. Okay, from here you can calculate your K, rearrange, and you can see here, okay, you can see here that your MS can cut. Okay, when you okay, I would like to draw your attention to this part here, all right? Okay, there's actually a missing 2 here, all right? So when there is a missing 2, actually I forgot to put in the 2, power of 2. So that means your unit should be M negative 2, S negative 1. So the units of K are actually in the 3rd order, all right? So there is a slight mistake there. I hope that you will take in, change inside your notes, right? So let's cut that. Okay, so there is a slight listed order, right? You can, what do you call, that also quite common, all right, where this question is more wholesome compared to the earlier question. It's very simple and straightforward. Now, usually, your exams and your tests will have questions like this, all right, where they give you an example of a reaction. So in this case, it is like F2 plus 2ClO2 to get 2FCl. CIO, all right? Okay, now, actually it should be, all right, okay? And so the kinetic data for the above reaction is shown below, okay? Experiment 1, 2, 3. So the first reactant, you can see that is 0.10, and the second reactant is 0.01, okay? And the initial rate is 1.2 times 10 power of -3. And the second run, you can see the first reactant is 0.04 and the second reactant is also 0.04. And the initial rate is 4.8. Okay. Now, in this reaction, hold on here. Yes. Okay, so sorry for that. I think this one here is wrong. So this should actually be, let me make the correction. I think in your notes, I have already made the correction, but somehow it is missing here. So never mind, let me just make the correction. Okay. All right, so this concentration here should be 0.0. This concentration here should be 0.20. Okay, now let's look at how we are going to solve this question. All right, so you can see that the first experiment and the second experiment, all right, it has the same concentration for the first reactant, and the second experiment and third experiment, okay, you can see that the concentration of the second reactant in the first experiment and the third experiment is now similar. Okay, so it is not always experiment 1, experiment 2, experiment 2, experiment 3. It can also be experiment 1, experiment 2, then experiment 1 and experiment 3. So it all depends on how do you want to manipulate your experiment or to create the what do you call the method for your experiment. Okay, so in this experiment we can see that they are actually keeping experiment 1 is a constant and they're changing 2 and 3. All right, now let's look at question A. Determine the order, okay, of the reaction with respect to the two reactants. All right, now let the rate equation be rate equals to K, reactant A, the first reactant, alpha, and second reactant, and beta, or B. All right, not alpha, we're using A and B. Okay, so comparing experiment 2 and experiment 1. Okay, so now you take experiment 2, you compare with experiment 1. Okay, so you have the initial rate for your experiment 2, right, and your initial rate for experiment 1. Okay, so what we're doing here is basically we take rate, okay, of your experiment 2 and you divide by the rate of your experiment 1. Okay, so from here you can see that, okay, experiment 2 and experiment 1, because the values for your first reactant are the same. So what we have done here is we didn't even put them in, all right? But actually you can put, but then even if you don't want to, then it is fine, okay? So you can just keep it to this, right? But it is still the same from what we did earlier. Okay, it will still be, if you want to write out, you can, all right? It will be 0.1, sorry. Okay. Just, okay. So if you want to, you can still write, okay, rate of your experiment 2, okay, divided by the rate of your experiment 1. Okay, so this will be equals to K, okay, and then your 0.01, right? And this is your A. Okay, and B, the value will be 0.04. Okay, right. And then you have your K, 0.01 A, and 0.01 B. Okay, so from here you can see that you can actually cancel off, okay, cancel off these two. All right, and you can put in the value for your experiment 2, the rate, and experiment 1, and you divide this way. Okay, so when you divide, you will get 4 equals to 4B. So from here, you know that B is power of 1. Okay, so you can do the same for comparing the experiment 3 and experiment 1. Okay, so you do the same for experiment 3 and 1, right? So now it is rate experiment 3, and then you divide by your rate of your experiment 1. Okay, the same thing, K 0.0, experiment 3 is 0.20, sorry. Okay, 0.20 A, and then experiment 3, sorry, experiment 3 is, okay, 0. Let's just try that. Okay, give us a bit more space, huh? So let's do that again. Rate of experiment 3 over the rate of experiment 1. Okay, so this is equals to K 0.20 A 0.01 B. Okay, over rate K experiment 1, 0.10, and A and B will be 0.01 B. Okay, so from here you can cut off B, cut off your K. So what you are left with is this. All right, so you're left with this. So from here you can divide and you can find that 2 equals to 2A. So again, A will become 1. So from this reaction, you know that the overall order is, right? You know that the overall order will be, okay, your overall order here is 1 plus 1. Okay, so 1 for A plus 1. Okay, so A plus B. That is your overall order. Okay, order of your reaction. Okay, so the reaction is first order with respect to both F2 and CaO. All right, now determine the second part is calculate the rate constant. Now that you know the order of the reaction, okay, now that you know that your rate now can be written as rate equals to K, and then it's F2, K, and then ClO2. Okay, both which are of first order reaction. So you must be able to write out this equation once you have determined the order of reaction. So from there, you can now calculate the rate constant. Again, you just choose any one of these experiments and you plug in the data. So now we are choosing experiment 1. So the initial rate for experiment 1 is 1.2 times 10 power of negative 3 equals to K. And then you can see here the concentration of F2 is 0.10 and the concentration of ClO2 is 0.01. Okay, from here you can calculate your K. Okay, again, don't forget your what you call units for your rate. Okay, and also the units of your what call this your each of your reactants. Okay, so overall order is 2. All right. Okay. All right. Now for C, now that you know the constant, the rate constant for C, they are asking you to calculate the initial rate when the concentration of F2 and ClO2 are 0.15 and 0.13 mole per dm cube respectively. Right? Okay. So from here you can see that the rate you already know 1.2 is your unit, and then 0.15 times by 0.03, which is given in your question. Okay. And just do a normal times, and then you can, of course, you need to take into consideration of your unit volume. Okay, so that is another example. All right. Now let's go to the next example. Okay, the next example will be slightly different. All right. Okay, so let's look at another example. All right. So consider the reaction of nitric oxide with hydrogen at 1280 degrees C. Okay, so you can see here your reactants are NO and H2, right? Your hydrogen. Okay, and then you have your initial rates. And you can see from here your experiment 1, it's 0.01 for both the reactants. Okay, and then experiment 2 is 0.02 and 0.03. And your experiment 3 is 0.01 and H2 is 0.02. Okay, now from here, your first task is to identify how are you going to compare the values. Okay, your first task is to identify how you're going to do the comparison of the values. Okay. To continue, right, we have to identify what is it that we want to compare. So in this experiment, okay, or this question, there's actually something very different compared to all the other examples that we have looked at so far. All right, so you can see here only one place where the concentration matches. Okay, for your experiment 1 and experiment 3, where the concentration is matching. And you can see here for the second species, the concentration are not matching to any. Okay, so there is also a way of getting past this kind of question. So we will look at it in detail. All right, so we from the question we know it's 2NO plus 2H2 to get N2 and 2H2O. So the rate law is given by rate equals to KNO X and H2Y. Okay, so this is common, and all of you must be able to write this, rate equation, okay, without any problems, right? So let's look at how to solve this question. Okay, so here I want to bring your attention, okay, to take the ratio, okay, of the rates run 3 and 1. Okay, just now we already saw only for experiment 3 and experiment 1, the NO concentration is fixed. Okay, so you write there, okay, this is the initial rate of your experiment 3 and initial rate of experiment 1. Okay, when you divide, you actually get 2. Okay, and then of course you can cut off this, right? And then you cut your K, right? And then you can cut this off too. Okay, you cut this off as well. Right? And then you are left with 2. All right, and this expression here, 0.02 y over 0.01 y. Okay, now this one we can change the form to become 0.02 over 0.01 y, right? And this is equals to 2. So when that happens, you log the whole thing. Okay, so you log on one side, log on another side. So log 2, you can find the answer. All right, and then of course when you have log, okay, 0.02 over 0.01 y, so your y can bring to the front. Okay, so this is the very common, very simple log what they call expressions that all of you must know already by now. Okay, so y equals to log 2 over log 2. All right, so this is one way to determine. So now you know that y is equals to 1. Okay, so now that you know y is equal to 1, so we can solve x in a similar way. Okay, so you can take rate of 1 divide by rate of 2. Right, and then you can have your K and OX of experiment 1, right, and H2 of experiment 1 over NO of experiment 2 and H2 of experiment 2. Okay, so you put all the values in. Okay, now you already know your Y is equals to 1. Correct? So your X you don't know. So it actually doesn't matter if you, the what do you call, the fact that these two are not the same. Okay, but they can differ. All right, when they differ, but you must make sure that you already know the order. So in that case, you already know when you divide these two, the order is 1. Okay, and then you can cancel your K here and cancel your K here, and you solve this equation. All right, 1 over 24. Okay, then here is time, so this is dy, and then you will get 1 over 2x equals to 1 over 3. Okay, so again, now you log both sides, and you can get your x is equals to log 1 over 8. All right, log 1 over 8 over log 1 over 2. Okay, and then you can get your x is 3. So from here, we now know what is your rate equation. So your rate equation now is rate equals to K. Okay, the first one is NO, right? Yeah, NO, the order is 3, and your hydrogen parameter is 1. Okay, so 1 you can write, or usually we don't write, but this is just for me to show you how to write the rate equation for this question. Okay, now that's simple. Okay, so bear in mind, sometimes you will not get a question where both the concentration for both the reactants are fixed at particular time. Okay, sometimes they only fix one, and you must be able to, to know or aware that it is okay. You can still find your answer. All right. So, to wrap up that question, so you can see here. All right. Okay, you can see that the rate law is written as this. So in order to find the rate constant, choose one set of data and you solve the equation. Okay, so you can see here. So power of 3 and this is power of 1, right? And you will get this as your rate constant. So you can have 0.012 over with 0.01 power of 3 times 0.002. There's an extra 0 here. This 0 shouldn't be there. Okay, so there will be some typos here and there. So you just be aware, and you can change it on your own as well. If I missed it, then you can change it on your own. All right. Okay, but mostly I will let you know if there is any typos in the slide. Okay, so that is simple. All right, now you know how to do it. Okay, we have done 3 different examples so far. Okay, next. So let's see what's next. So next is all right. So next is now we will break out into our breakout rooms as usual. All right, and you will be given some time to quickly answer the question. Questions are very easy, in fact, because we already go through step by step of each type of question that is possible. All right, so these 2 questions is very easy. So once you go into your breakout rooms, quickly prepare the answer, and I will choose 2 groups to present the answer. Okay, so I will go in to check all of your answers in a while. Okay, I will give you time to do it first. Then I will go in to check, and then when we come back, 2 groups will be presenting. 1 group will present question 1, 1 group will present question 2. Okay, so Dr. Galo, if I can ask for your help here, can prepare the groups for what do you call breakout rooms. Okay, as usual, our students will be group 1 to 5, 7 students per group. The rest can be in other groups. Yeah, thank you.
Okay, dokter. So I already assigned 10 breakout rooms. Sudah ada ya 10 breakout room. Silakan memilih grup 1 sampai 5 untuk registered student, untuk mahasiswa yang memang terdaftar ya pada perkuliahan. Kemudian yang grup 6 sampai 10 sisanya untuk yang sit in ya. Jadi silakan, sudah saya buka breakout room-nya. Sudah bisa dipilih ya?
Done, Doctor. Thank you.
Okay, thank you.
Everybody's going to group 3. I will remove some of them from group 3.
Group 1 is always the last to fill.
Okay, I think they are all in their groups.
Mhm.
Okay, yeah. So I give them a bit of time to try the 2 questions, then I will go in and check.
Mm.
Yeah.
I will move some student from room 9. Sorry, from room 10. So many of them.
Seems like our group also they keep changing, they keep jumping.
Yeah, because they realize that the group is too
Their friend is not
many
they
people,
jump.
or they're looking for their friends.
I think so. They're looking for their friends.
Yeah.
I'm going to just take a toilet break for a while. Now we're going to
Mhm.
them. Yeah.
Hi, hello.
Well, yes. Uh,
Okay, so now that everyone is back, can we see two groups? Okay, which two groups want to volunteer? Between group 1 to group 5, which two groups would like to volunteer? For question number 1, which group did I say just now you got it right? Okay, can we have one group to volunteer? If not, I will choose. Anyone? Okay, never mind. Then I will choose. Group 2 will be presenting question 1, and group 5 can present question 2. Okay, quickly, group 2, can we see your answer to question 1? Okay, question 1 is actually very simple. You don't have to think too much. It's actually a very simple maths. All right. Okay, so can we have the answer from group 2?
Okay, Dokter.
Yes.
Salma, please. Okay, my discussion to question 1 and to find is the rate reaction 0, first, and second, and we find rate to 0 order is rate some rate is constanta, and first order kinetic rate is 0,75 constanta, and second order kinetic is rate 0,5625 constanta. So the constanta not calculate, and it's very simple. Ada yang mau ditambahin, teman-teman?
Okay, good try, group 2. But there is actually a slight mistake, but never mind. Let me explain. Okay, but good try. Good try. Okay, let me share my screen. Maybe you can stop to share so that I can share my screen.
Okay.
Okay. So the question 1 is actually more of, we can say, like a trying to trick kind of question. All right. Actually, it's more of a mathematical instead of anything. What we are trying to say is, okay, let me write it up for you. Okay. So hold on, yeah. Okay, now what we are trying to say is actually 0. What is happening? Okay, hold on for a while. My computer jammed for a while. All right. Okay. Okay. What we are trying to say is 0.25. Okay. You get 1.7 times by 10 power of -4. Okay. So what we want to know is when it is 0.75. Okay. How will the rate differ? Okay. Now, because first one is the 0 order kinetic, so there is no difference. So it will still be 1.7 times 10 power of -4. Okay. For B, it is 0.75. Okay, times by 1.7 times 10 power of -4. Okay, divide by 0.25. Okay, because it is first order. Okay, this is B, right? And C, okay, because it is second order, so the same thing, but now we can power of 2 times by 1.7 times 10 power of -4. We are basically just trying to show how it will differ in terms of when you increase the order of reaction. That's all. So it's more of like mathematical question, all right, instead of a rate question. Okay, can now?
Baik.
Okay.
Thank you, Dokter.
All right, thank you. So let's have a second group 5. Can you share with us the answer for the second question so that we can end the class today after the next group shares the answer? Barik's group, right? Group 5. Can you share the answer for number 2?
Actually, ma'am, I am from group number 5 and we still only do question 1 mistake that it will clear and we are unable to do question number 2.
Oh, okay. Then can we have another group instead? Maybe we
Yes,
can
Doctor,
have-
I'm sorry. We
It's okay.
haven't finished yet. The
It's
question number
okay.
2.
Okay, can we have question 2 by group number 3 then? Group 3, can you show us the answer then? Is it possible? Or you guys haven't finished it as well? If you haven't finished, maybe what we can do is you can upload the answer to Padlet, maybe in groups, right? Okay, so never mind. Okay, if you haven't finished, all right. So let's keep question number 2 as a group work for you to upload into Padlet. Okay, please upload the answer for question number 2. And then next week, before we start the class, I will just choose one of the answers and then we can go through it. Okay, is that okay? All right. Can,
Right.
Okay, Doctor.
Okay, thank you everyone. See you next week. Have a good day.
Thank you, Dokter.
Bye.
Thank you, Doctor. See you, everyone.
Bye, Dr.
Yes.
Galuh. Thank
Thank you
you.
very much, Dr. Galuh and Dr.
Terima
Sangeetha.
kasih, Bu.